Look up at the night sky, really look at it. Countless stars twinkle back at you, steady and unchanging, as they have for millennia. But what if one of them suddenly winked out? What if a star that had shone brightly for generations simply vanished? This isn't just science fiction. Astronomers have witnessed stars dimming inexplicably, their light blocked by something massive, something we can't yet explain. And that's where things get even stranger. Some scientists believe these mysterious disappearances could be evidence of alien megastructures, colossal engineering projects built by civilizations far more advanced than our own. Think about that for a moment. Entire stars concealed by technology so vast it defies human comprehension. The idea of alien megastructures isn't just wild speculation. It's rooted in real scientific curiosity, a quest to explain the unexplainable. When a star's light flickers or fades without warning, astronomers scramble for answers. Could it be a swarm of comets, a rogue planet, or something far more extraordinary? Imagine a civilization capable of harnessing the energy of an entire star, building a Dyson sphere, a shell of solar panels encircling it, or a massive array of orbiting platforms. These megastructures would block starlight in ways that natural phenomena simply can't replicate. The implications are staggering. If we found one, it wouldn't just rewrite astronomy textbooks, it would change everything we thought we knew about our place in the universe. This is the thrilling frontier we're about to explore together. Over the next few minutes, we'll journey into the cutting-edge science behind these cosmic mysteries. We'll examine the most baffling star-dimming events ever recorded, dig into the theories that could explain them, and ask the biggest question of all: are we alone? Whether you're a seasoned space enthusiast or just someone who's ever gazed up at the stars and wondered, this video is for you. Because the search for alien megastructures isn't just about distant suns and hypothetical civilizations, it's about pushing the boundaries of human knowledge. And who knows, by the end, you might find yourself looking at the night sky a little differently, questioning what else might be out there waiting to be discovered. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars. Given the sheer numbers, it seems almost certain that intelligent life must exist somewhere beyond Earth. Yet here we are, surrounded by silence. This baffling contradiction is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the cosmos is so full of potential, why haven't we found any traces of alien civilizations? One unsettling answer lies in the very stars we've been watching blink out. Think about our own technological trajectory. In just a few centuries, humanity has gone from steam engines to space telescopes. Now, imagine a civilization thousands or even millions of years ahead of us. Their energy needs would be colossal, far beyond what fossil fuels or even nuclear power could provide. That's where megastructures come in. A truly advanced civilization might harness the energy of their star by building a Dyson swarm, a network of orbiting solar collectors, or even a solid shell enveloping it. But these enormous constructs would inevitably block starlight, making their sun appear dim or vanish entirely from our telescopes. This might solve part of the Fermi Paradox. We're not hearing alien radio signals or spotting their interstellar probes because, quite simply, the most advanced civilizations could be hidden in plain sight, cloaked by their own technology. Their stars wouldn't shine the way we expect. Instead of beacons in the dark, they might be shadows. When astronomers detect a star inexplicably fading, they're not just looking at a cosmic oddity. They might be glimpsing the handiwork of an intelligence so advanced it bends the laws of physics to its will. Of course, not all disappearing stars are proof of alien engineering. Nature has its own ways of dimming starlight, dust clouds, planetary debris, or even rare cosmic alignments. But the possibility remains tantalizing. If a star's light dips in a way that defies natural explanations, scientists take notice. Each unexplained dimming event could be a breadcrumb trail leading us toward one of the greatest discoveries in human history. So when we ask, where is everybody, the answer might be staring us right in the face, or rather, hiding in the darkness between the stars. Let's start with the granddaddy of alien megastructures, the Dyson Sphere. Dreamed up by physicist Freeman Dyson in the 1960s, this colossal feat of engineering would be the ultimate power source for a civilization hungry for energy. Picture a shell of solar panels or mirrors completely encircling a star, capturing every last photon of its light. From our vantage point on Earth, such a structure would transform a brilliant sun into something far stranger, a dim, flickering anomaly in the night sky. But why would an advanced civilization build something so unimaginably vast? Think about humanity's own energy consumption. In just a few centuries, we've gone from burning wood to splitting atoms. Now imagine a society 1,000 or even 1,000,000 years ahead of us. Their energy needs would dwarf ours, requiring not just more power, but an entirely new scale of infrastructure. A Dyson sphere would allow them to harness every drop of their star's energy, no wasted sunlight, no untapped potential. It's the difference between cooking over a campfire and controlling the entire bonfire. Of course, building a solid shell around a star is mind-bendingly difficult. The gravitational forces alone would be catastrophic unless the structure were perfectly balanced, and the materials required don't even exist in nature, at least not that we know of. That's why many scientists now favor the idea of a Dyson swarm, a cloud of smaller, independent energy collectors orbiting the star in a dense formation. Think of it like a fleet of billions of solar-powered satellites working in unison to siphon off starlight. To an outside observer, the effect would still be dramatic. The star wouldn't vanish completely, but its brightness would dip unpredictably as the swarm shifted and realigned. This is where real-world astronomy gets fascinating. In 2015, astronomers spotted a star called KIC 8462852, later nicknamed Tabby's star, behaving in ways no natural phenomenon could easily explain. Its light dimmed by as much as 22% at irregular intervals with no clear pattern. Dust clouds too inconsistent, a planet far too extreme. For a brief, exhilarating moment, some researchers wondered if we might be looking at a partially built Dyson swarm, while later studies leaned toward natural explanations like interstellar debris. Tabby's star remains a tantalizing mystery. Because here's the thing, even if this particular anomaly isn't proof of alien engineering, it's a blueprint for what to look for. If a Dyson swarm exists somewhere in the cosmos, its signature would be unmistakable. A star that flickers like a candle in the wind, its light scattered by something vast, deliberate, and utterly artificial. The hunt isn't just about finding megastructures, it's about learning to recognize the fingerprints of intelligence on a cosmic scale. And that's what makes this search so thrilling. We're not just waiting for aliens to call us on some interstellar telephone. We're scanning the heavens for the shadows they might cast, literal shadows carved into the light of distant suns. Whether it's a Dyson sphere, a swarm, or something even more unfathomable, the truth is out there. We just have to keep looking. Now let's peel back the layers of these megastructures, because not all Dyson spheres are created equal. The classic image, a solid, seamless shell encasing a star, is just one possibility, and frankly, it's the most sci-fi version. In reality, the physics of building something like that is mind-bogglingly complex. The material strength required to withstand a star's gravity, heat, and radiation without collapsing or melting is beyond anything we know. Even if such materials existed, maintaining structural stability would be a nightmare, like trying to balance a marble on a needle while floating in space. That's why many scientists think a Dyson swarm is far more plausible. Instead of one gigantic shell, imagine millions or even billions of smaller energy-harvesting satellites, each orbiting the star like bees around a hive. Here's where things get really interesting. These two designs would look dramatically different from our vantage point. A solid Dyson shell would block starlight almost completely, turning a blazing sun into little more than a faint infrared glow, the waste heat leaking from the structure. It'd be like wrapping a light bulb in black cloth. The brightness plummets, but a Dyson swarm, that's trickier to spot. The star's light would dip and flicker unpredictably as the swarm's components drift in and out of alignment. Sometimes a chunk of satellites might pass in front of the star, causing a temporary dimming. Other times, gaps in the swarm could let bursts of light through. It'd be less like flipping a switch and more like watching clouds drift across the sun, a dance of shadows with no set rhythm. This distinction matters because it shapes how we search for these megastructures. If we're looking for a solid shell, we'd hunt for stars that emit almost no visible light but still radiate heat. Infrared telescopes like NASA WISE have already scoured the sky for such anomalies. But a swarm that requires patience, we'd need years of observations to catch its irregular dimming patterns, ruling out natural explanations like planets or dust. Tabby's star, with its bizarre, unpredictable dips, gave us a taste of what that might look like. Whether it's a swarm or not, the takeaway is clear. Alien megastructures wouldn't just hide stars. They'd make them behave in ways that defy the usual cosmic rulebook, and that's the real thrill of this hunt. We're not just staring at the sky waiting for a neon sign that says aliens here. We're learning to read the subtlest clues, the way a star's light stutters, the heat it leaks, the shadows it casts. Whether it's a swarm of satellites or an unthinkable solid shell, each design leaves its own fingerprint. The universe is stranger than fiction, and the truth might be hiding in the flicker of a distant sun. Imagine taking the Dyson sphere concept and cranking it up to 11, not just harnessing a star's energy, but transforming it into the ultimate supercomputer. That's the mind-bending premise behind Matrioshka Brains, named after those iconic Russian nesting dolls. These hypothetical megastructures wouldn't just encase a star, they'd layer around it like a cosmic onion, each shell designed to capture and utilize the waste heat of the layer above. The innermost sphere might absorb the star's raw radiation, converting it into computational power, while outer layers would process the residual energy, creating a cascading network of unimaginable processing capability. Here's the genius of the design. Every layer would operate at a different temperature. The innermost shell, blisteringly hot from the star's output, would handle the most energy-intensive calculations. As heat trickles outward, each subsequent layer would use the diminishing thermal energy for less demanding tasks, like long-term data storage or background processes. It's the ultimate efficiency hack. A civilization could theoretically harness nearly all of a star's energy, not just for electricity, but for pure information processing. The waste heat alone would glow in the infrared spectrum, making these structures detectable across interstellar distances as bizarre, heat-radiating objects with almost no visible light. But what would a Matrioshka brain actually look like from Earth? Unlike a traditional Dyson sphere, which might block starlight uniformly, these nested layers would create a more complex fingerprint. The outermost shell, cooler and likely partially transparent, might let faint traces of light escape, while the inner layers would scatter and absorb the rest. The result, a star that appears unnaturally dim, flickering with irregular patterns as computational processes shift energy between layers. Imagine a campfire smothered under layers of mesh screens. Some light gets through, but in unpredictable, patchy ways. The implications are staggering. A single Matrioshka brain could perform calculations so vast they dwarf human comprehension. We're not talking about running advanced simulations or cracking encryption. This would be a system capable of modeling entire universes, solving problems at scales we can't even fathom. Some theorists suggest such a structure could host uploaded alien consciousnesses, creating a digital afterlife or even a hive mind spanning solar systems. The energy demands of such a project would be catastrophic for a planet-bound civilization, but trivial for a society that's mastered stellar engineering. Of course, nature loves throwing curveballs. Before we jump to aliens, astronomers have to rule out more mundane explanations like rogue dust clouds or bizarre stellar physics for any weird starlight patterns. But the hunt for these nested megastructures isn't just science fiction. Projects like the Breakthrough Listen initiative already scan the cosmos for unusual infrared signatures, and next-gen telescopes could spot the telltale heat glow of a Matrioshka Brains' outer layers. Think about it, if we ever found one, it wouldn't just be proof of aliens. It'd be evidence of a civilization so advanced they've turned their sun into a thinking machine. That's the wildest part of this search. We're not just looking for life, we're looking for minds that might be so different from ours, they've redefined what intelligence even means. And out there in the dark, something might already be watching us back, not with eyes, but with the cold, calculating gaze of a star-sized supercomputer. What if an advanced civilization didn't just build around their star, but decided to move it? That's the jaw-dropping premise behind stellar engines, megastructures so powerful they could literally push a star across the galaxy. The most famous design, the Ashkadov thruster, sounds like something straight out of a sci-fi epic. Picture this, a gargantuan mirror, half the size of a solar system, positioned just close enough to a star to harness its own light as propulsion. Here's how it works. The mirror reflects a portion of the star's radiation, creating an imbalance in energy output. The star's light pushes against this cosmic sail, gradually nudging the entire system in the opposite direction. It's like using a flashlight to push yourself through space, except the flashlight is a sun, and you've got billions of years to reach your destination. Now, here's where things get eerie for astronomers. While an Ashkadov thruster is in operation, the star's light wouldn't just dim, it would become lopsided. From Earth's perspective, the side with the massive mirror would appear darker, as if someone had taken a bite out of the sun. Over centuries, this asymmetry could shift as the star changes course, creating a telltale signature in telescopic data. Imagine watching a star that brightens and fades rhythmically, not because of orbiting planets, but because it's being steered by forces beyond nature. But why would anyone want to move a star? The reasons are as vast as space itself. Maybe a civilization foresees a deadly supernova and relocates their home system to safety. Perhaps they're navigating toward richer galactic neighborhoods brimming with resources. Or, in the most mind-bending scenario, they could be assembling multiple stars for an unfathomable energy project, cosmic engineering on a scale that redefines the word ambition. The implications for detection are thrilling. A star under propulsion wouldn't just flicker, it might drift across the sky at unnatural speeds, trailing a faint infrared glow from the thruster's waste heat. Even stranger, if multiple civilizations were using these engines, we might spot entire clusters of stars moving in coordinated patterns, like a celestial ballet choreographed by unseen hands. Of course, nature has its own ways of hurling stars through space. Close encounters with black holes or galactic collisions can send suns careening. But a star moving precisely, with its light distorted in ways that mirror theoretical blueprints. That's the kind of anomaly that would set astronomers' hearts racing. We're not just hunting for alien structures anymore. We're searching for the wake of stars that might have been pushed, evidence that somewhere, someone is rearranging the cosmos itself. The Great Filter stands as one of the most haunting ideas in our search for cosmic neighbors. It suggests that somewhere between the emergence of life and the rise of galaxy-spanning civilizations, there's a barrier, a catastrophic challenge so severe that almost no species survives it. This could explain why the universe seems so eerily empty despite its overwhelming vastness. But here's where alien megastructures add a chilling twist. They might not just be evidence of advanced life, they could be the smoking gun of civilizations that did get past the Great Filter. Or worse, they might be the ruins of those that didn't. Think about humanity's trajectory. We've harnessed fire, split the atom, and touched the edges of our solar system. But we're also teetering on existential threats: climate collapse, nuclear war, rogue AI. Now imagine a civilization just a few centuries ahead of us, grappling with energy crises or technological runaway. Building a Dyson swarm could be their salvation, a way to secure infinite power and escape planetary dependency. But what if it's also their doom? Megastructures of this scale aren't just engineering projects, they're existential gambles. One miscalculation, a swarm collapsing into its star, a Matrioshka brain overheating, and suddenly, a once great civilization vanishes, leaving only a flickering star as its tombstone. There's another, darker possibility. The Great Filter might not lie in the past at all. It could wait for us and every other civilization after the stage of megastructures. Imagine a universe where advanced species inevitably hit a ceiling, where the very technologies meant to save them, stellar engines, AI networks, planetary disassembly, become their undoing. The eerie silence of the cosmos wouldn't be because life is rare. It'd be because intelligence always self-destructs when it reaches a certain scale. Yet there's hope in the shadows. If we do find a functioning megastructure, it proves the Great Filter can be beaten. A single intact Dyson swarm would mean that at least one civilization out there made it harness the stars without collapsing under their weight. That's why the search for these cosmic artifacts isn't just academic. It's a race to answer the most urgent question of all. Are we alone because life is fragile, or because the universe is littered with the wreckage of those who came before us? The silence of the cosmos might not be emptiness. It could be a warning or a challenge. Every anomalous dimming star we find is a clue, a piece of cosmic archaeology. And the stakes couldn't be higher. If the Great Filter is ahead of us, then finding or not finding alien megastructures isn't just about curiosity, it's about survival. Tabby's star isn't just another flickering dot in the cosmos. It's a cosmic detective story with more twists than a thriller novel. Officially dubbed KIC 8462852, this unassuming star, nestled in the constellation Cygnus, first made headlines in 2015 when astronomers noticed its bizarre behavior. Unlike the predictable dimming caused by orbiting planets, Tabby's star's light would plunge by staggering amounts, up to 22% at times, in irregular, almost chaotic patterns. Imagine watching a lamp in your house suddenly dim to a flicker, then brighten again with no rhyme or reason. That's the kind of anomaly that sends scientists scrambling for explanations. At the heart of the mystery is a tantalizing question. What could possibly block a star's light so dramatically? Early theories ranged from the mundane to the extraordinary. Maybe it was a colossal swarm of comets, their dusty tails casting fleeting shadows, or perhaps an interstellar dust cloud drifting unpredictably between us and the star. But these natural explanations hit snags. Comets couldn't account for the sheer scale of dimming, and dust would typically scatter light in ways that didn't match the observations. That's when the megastructure hypothesis took center stage. Could this be evidence of a partially built Dyson swarm, a vast array of alien solar collectors orbiting the star, intermittently blocking its light? The idea wasn't just plausible, it was electrifying, but science thrives on skepticism, and Tabby's star became a battleground of competing theories. Later studies suggested that uneven dust clouds, possibly from shattered planets or asteroid collisions, might explain the star's odd flickering. The dust wouldn't behave like typical interstellar material. It could be clumpy, irregular, and dense enough to cause those extreme dips. Infrared observations added weight to this idea, detecting heat signatures consistent with dust rather than the cold, metallic surfaces of a megastructure. Yet even now, the puzzle isn't fully solved. The dust explanation fits many of the observations, but not all. Some dimming events remain stubbornly inconsistent, leaving the door cracked open for more exotic possibilities. What makes Tabby's star so compelling isn't just the unanswered questions. It's the blueprint it offers for future discoveries. This star taught astronomers what to look for: anomalies that defy textbook explanations, patterns that whisper of something stranger. Whether it's aliens or an undiscovered natural phenomenon, the lesson is clear. The universe is wilder than we imagine, and the next time a star winks at us unexpectedly, we'll know to look closer. Because sometimes the most ordinary-looking twinkle in the sky holds the most extraordinary secrets. Tabby's star might be the poster child for mysterious dimming, but it's far from alone in the cosmic lineup of oddities. Take Epoch 204278916, a young star in the Scorpius constellation that left astronomers utterly baffled. Over the course of just one day, this star's light plummeted by a jaw-dropping 65%, like someone slowly turning a dimmer switch before snapping it back to full brightness. No known natural phenomenon, not planets, not dust clouds, explains such an extreme, rapid drop. Even more intriguing, the dimming wasn't symmetrical. It happened in jagged, uneven steps, as if something with an irregular shape, maybe a swarm of megastructures in chaotic orbit, was drifting in front of the star. Then there's VVVWIT-07, a giant star in our Milky Way that behaves like a cosmic peek-a-boo champion. For over 200 days, it faded until nearly 90% of its light vanished, only to gradually return over the next few hundred. That's not just unusual, it's unprecedented. Planets transit in hours or days, dust disperses, but something blocking a star's light for months. That suggests an object of staggering scale, perhaps a vast, opaque disk or a fleet of artificial shadows moving at a glacial pace. What ties these stars together isn't just their strangeness, it's how they defy easy classification. Epoch 204278916's rapid, lopsided dimming resembles what you'd expect from a fragmented Dyson swarm under construction, with panels only partially blocking light. VVVWIT-07's slow, dramatic fade aligns more with a SH-Kadov thruster's massive mirror or a Matrioshka Brains' outer shell, obscuring the star in deliberate, long-term cycles. Neither fits the tidy patterns of natural astrophysics, yet both tease us with possibilities just beyond our grasp. But before we declare these as alien engineering, science demands caution. Epoch 204278916 is a young star prone to violent flares and surrounded by swirling debris, perhaps a protoplanetary disk tilted at a bizarre angle, casting erratic shadows. VVVWIT-07 might be shrouded by a super-sized version of Saturn's rings, a natural if freakish cosmic filter. The key is in the details: the infrared glow, the light's polarization, the way shadows shift. Each clue peels back another layer, revealing either nature's infinite creativity or something far more extraordinary. That's the exhilarating tension of this search. Every anomalous star forces us to stretch our imaginations, to ask, is this the one? The universe doesn't give up its secrets easily, but with each flicker, each unexplained dimming, we're learning to read between the lines of starlight, and one day we might just find the message written there. Detecting alien megastructures isn't as simple as spotting a star that flickers. Nature has its own bag of tricks, cosmic phenomena that mimic the very signals scientists hope might reveal advanced civilizations. Take young stars, for example. Many are surrounded by thick disks of gas and dust, the raw materials for planet formation. These disks aren't smooth like vinyl records. They're lumpy, pockmarked with gaps where planets carve their orbits. When those clumps pass between us and the star, the light dips erratically, almost like something artificial is blocking it. Even mature stars aren't off the hook. A rogue swarm of comets, hundreds of thousands strong, could create a similar pattern of irregular dimming. The challenge: telling the difference between a natural cosmic spectacle and the shadow of intelligence at work. The devil's in the details, or more precisely, in the light itself. Natural obstructions like dust leave fingerprints that artificial structures don't. Dust scatters shorter wavelengths of light blues and ultraviolet more than longer red and infrared waves. So when a star dims because of dust, it doesn't just get fainter, it subtly reddens like sunlight filtering through wildfire smoke. A solid megastructure, by contrast, would block all wavelengths equally, turning the star uniformly dim without altering its color. That's why telescopes like Hubble and James Webb don't just measure brightness. They dissect starlight into a rainbow of wavelengths, hunting for these telltale spectral clues. Then there's the matter of timing. Planets orbit their stars with clockwork regularity. You could set your watch to their transits, but a Dyson swarm under construction. Its shadows would be chaotic, with dips occurring at uneven intervals as new panels are added or orbital paths shift, even more revealing the shape of the dimming. A planet's transit creates a symmetrical U-shaped light curve as it smoothly blocks and unblocks the star. A swarm of megastructures, though, might produce jagged, asymmetrical dips, like watching someone pass through a picket fence rather than a single solid gate. But nature loves to blur the lines. Some stars, like the infamous plywood star, EPIC 203820627, show dimming patterns so bizarre they defy categorization. Its light curves resemble a staircase, sharp drops followed by plateaus, as if something with hard, geometric edges is orbiting it. While a fractured Dyson ring could explain this, so could a tilted disk of debris with dense, angular clumps. The key is context. Astronomers cross-check every anomaly against other data. Infrared heat signatures, megastructures should irradiate absorbed starlight as warmth. Stellar-age older stars are less likely to have leftover planet-forming debris and even gravitational wobbles that might betray unseen planets. Perhaps the most tantalizing cases are the ones that resist all natural explanations. When every test rules out dust, every model excludes planets, and the star's behavior still screams unusual, that's when the megastructure hypothesis gains traction. It's not about jumping to aliens, it's about methodically eliminating the impossible. Because out there in the dark, amid the swirling dust and rogue comets, there might be one star whose shadows move in a way only intelligence could design. And when we find it, the universe will seem a little less lonely and a whole lot stranger. A star's light tells a story, not just of nuclear fires burning in its core, but of anything that passes between it and us. Planets, for instance, leave clean, predictable signatures when they transit. Their round shapes carve symmetrical dips in the star's brightness, like a pebble dropped into a stream creating a perfect ripple. But a megastructure, that's where the cosmic plot thickens. Imagine a colossal solar panel, a jagged orbital ring, or a fragmented Dyson swarm drifting across the face of a star. These aren't smooth, spherical objects. They're uneven, geometric, even haphazard. And that irregularity would paint a wildly different picture in the data. Take a giant solar panel as an example. Unlike a planet which blocks light uniformly, a flat, angular structure would cast a shadow with hard edges. The star's brightness wouldn't fade smoothly in and out. It would drop sharply, like flipping a switch, then hold steady before snapping back just as abruptly. Telescopes like Kepler or TESS, designed to hunt for planets, would flag this as bizarre. A planet's transit looks like a gentle U-curve. A megastructures might resemble a staircase or a series of jagged cliffs. Now picture something even more complex, a rotating ring of habitats or collectors encircling a star at a tilt. As it spins, different sections would block the star's light at varying angles, creating a light curve that pulses erratically. One orbit might show a deep dip as a thick segment transits, while the next reveals only a shallow dimming from a thinner edge. The pattern wouldn't repeat neatly, like watching a wobbly, misshapen wheel turn in front of a flashlight. And then there's the question of scale. A planet might block 1% of a star's light, but a megastructure could obscure 20, 50, even 90%. Imagine a star that nearly vanishes for hours or days, its light snuffed out by something vast enough to eclipse it partially. Even stranger, some designs like a louvered Dyson Swarm with movable panels might produce dimming that changes over time as sections open and close to regulate energy capture. The star's light wouldn't just dip, it would flicker like a candle in the wind, responding to unseen commands. Here's the kicker: natural phenomena rarely mimic these patterns. Dust clouds scatter light unevenly, but they also redden it as shorter wavelengths get absorbed. A solid megastructure wouldn't. A swarm of comets might cause irregular dips, but their debris trails would glow in infrared, something a sleek, metallic solar collector wouldn't do. The universe is messy, but intelligence leaves sharper fingerprints. That's why astronomers scrutinize not just how much a star dims, but how it dims. The shape of the light curve, the color of the filtered starlight, even the star's own age and stability. All these clues help separate cosmic oddities from potential technosignatures. It's forensic astronomy, really. Every anomalous dimming is a crime scene, and the light curve is the smoking gun. The shadows we're chasing might not just reveal megastructures, they could reveal the logic, the intent behind them. Because when you're looking at a star that flickers like a machine, you're not just seeing an object, you're seeing a mind at work. A Dyson sphere doesn't just vanish a star's light, it transforms it. Remember, energy can't be created or destroyed, only converted. So when an advanced civilization wraps a star in solar collectors, all that captured starlight doesn't just disappear. It gets used for computation, for propulsion, for cities beyond our imagining, and whatever isn't utilized radiates away as waste heat. That heat glows in the infrared spectrum, creating a cosmic fingerprint hotter than the cold void of space but far dimmer than the star itself. It's like holding your hand near a light bulb that's been turned off. You can't see the glow anymore, but you still feel the warmth. That's exactly what telescopes like NASA's A Wise Mission are hunting for. Not the absence of light, but the presence of something unnaturally warm where a star should be. This infrared signature is the smoking gun of megastructures. Natural objects, dust clouds, rogue planets, even failed stars emit infrared too, but their heat follows predictable patterns. A Dyson sphere, though, its thermal profile would be bizarrely artificial. Picture a star that emits almost no visible light but radiates infrared at temperatures far higher than background space. The numbers tell the story. A typical sun-like star blasts out light at around 5,500 degrees Celsius. A Dyson sphere's waste heat might hover around 300 degrees room temperature by cosmic standards, but blazing compared to the near absolute zero chill of the interstellar void. That mismatch, a star-sized object glowing gently in infrared, would stand out like a campfire in a snowstorm. Surveys like WISE scan the sky for these thermal anomalies, sifting through millions of data points. They found plenty of naturally warm objects, young stars cocooned in dust, colliding galaxies, even failed stars called brown dwarfs. But hidden in that sea of data could be something stranger. One tantalizing candidate is TSE 400799204, a strange object spotted in 2021. It emits no visible light, yet its infrared glow suggests something far larger than a planet. Some researchers proposed it could be a rogue Dyson sphere, untethered from its star. Others argue it's more likely a distant galaxy obscured by dust. The debate rages on, but the method is clear. Infrared astronomy lets us peek behind the cosmic curtain, searching not for what's brightly lit, but for what's quietly, suspiciously warm. The brilliance of this approach is that it sidesteps the limitations of visible light. A Dyson swarm might only block a fraction of a star's brilliance, making it hard to spot in optical telescopes. But its waste heat, that's unavoidable. Even a civilization capable of stellar engineering couldn't break the laws of thermodynamics. The energy they harness must go somewhere, and that somewhere is infrared radiation pulsing into space like a heartbeat. Of course, nature loves to mimic intelligence. Some stars, like carbon-rich red giants, shed dusty envelopes that glow faintly in infrared. Others are shrouded in debris disks that radiate warmth. The key is context. A true Dyson Sphere candidate wouldn't just be warm, it would be too warm for its surroundings without the chemical signatures of natural dust or gas. That's why projects like GHT, glimpsing heat from alien technologies, don't just look for heat, they analyze its spectrum, hunting for the unnatural uniformity of engineered materials rather than the jagged emissions of cosmic chemistry. The hunt is slow, painstaking work, but imagine the payoff. A star that ticks every box: no visible light, unnatural infrared warmth, no plausible natural explanation. That wouldn't just be evidence of aliens, it'd be proof that somewhere someone has tamed a sun, and the glow we'd detect, that's not just waste heat. It's the echo of a civilization powerful enough to rewrite the rules of the cosmos. What if the most compelling evidence of alien technology wasn't around their stars, but right above their planets? Picture Earth's orbit, cluttered with thousands of satellites forming a bustling network of communication, weather monitoring, and GPS. Now imagine that infrastructure multiplied by 1,000,000, a dense swarm of artificial objects encircling an alien world like a high-tech shroud. This is the idea behind Clark exobolts, named after sci-fi legend Arthur C. Clarke, who first speculated about geostationary satellites back in the 1940s. These megastructures wouldn't be built around stars, but around habitable exoplanets, forming a telltale technological halo visible from light years away. Here's how it might work. Every satellite, space station, or orbital habitat reflects a tiny fraction of its host star's light. Individually, they're invisible to our telescopes. But en masse, they'd create a faint, consistent dip in the planet's brightness, a subtle fingerprint of activity. Unlike natural phenomena like dust rings or moons, which tend to scatter light unevenly, an exobolt's artificial swarm would block starlight with eerie regularity. The more satellites, the deeper the shadow. A civilization just a few centuries ahead of us could easily have millions of objects in orbit, turning their planet into a flickering beacon among the stars. Detecting such a signal wouldn't be easy, but it's not impossible. Modern observatories like the James Webb Space Telescope are already capable of spotting exoplanet atmospheres by analyzing the light that filters through them. An exobolt would leave a different kind of mark, not the chemical signatures of gases, but the statistical noise of countless tiny obstructions. Imagine holding a sheet of paper with thousands of pinpricks up to a light bulb. From a distance, the bulb wouldn't just dim, it would shimmer, its light frayed by countless artificial edges. That's what astronomers might see as an exoplanet transits its star, its silhouette dotted with the angular shadows of satellites. The implications are staggering. A Clark exobolt wouldn't just hint at life, it'd scream industrial civilization. Natural cosmic debris fields like Saturn's rings have smooth, predictable structures. But an exobolt's density, distribution, and even its gaps, zones cleared for spacecraft traffic, could betray patterns only intelligence creates. Some researchers suggest looking for synchronized orbits, artificial clusters that maintain precise spacing, like a cosmic subway system. Others propose hunting for unnatural materials in the light spectrum, like the glint of solar panels or the heat signature of thruster burns. There's a poetic irony here. Humanity's own satellite swarms, Starlink, OneWeb, and their successors, are already beginning to alter Earth's reflectivity from space. In a few centuries, our planet might sport its own faint exobolt, visible to any alien astronomers scanning our solar system. The very technologies that connect us could one day be our first interstellar hello, or the last traces of a civilization that never quite made it further. Either way, the lesson is clear. Sometimes the most telling signs of life aren't found on worlds but around them. And as our telescopes grow sharper, we might just spot a distant planet winking back at us, its light threaded through with the artifacts of another mind's ambition. If Dyson spheres feel like cosmic-scale engineering, then black hole megastructures are where physics meets pure fantasy, or at least what looks like fantasy until you run the numbers. Picture this, a civilization so advanced they've outgrown stars entirely and turned their attention to the universe's ultimate energy sinks, black holes. These gravitational monsters don't just bend light, they devour it, and for a species craving unimaginable power, that's not a drawback, it's a feature. Start with the accretion disk, that swirling maelstrom of superheated gas and dust spiraling into oblivion. For us, it's a deadly inferno. For a Type 3 civilization, it's a power plant. Theorists like physicist Freeman Dyson, yes, the same mind behind Dyson Spheres, have speculated about accretion disk farms, a vast arrays of energy collectors hovering at the disk's edge, harvesting its furious radiation. The numbers are staggering. A single stellar mass black hole's disk can outshine entire galaxies in X-rays and gamma rays. Capture even a fraction of that, and you've got enough energy to fuel interstellar empires for eons. But here's the eerie part for astronomers. A fully harnessed black hole wouldn't look like a black hole. Normally, we detect these voids by their glowing disks or jets of plasma screaming into space. A civilization mining that energy would effectively turn off the lights, redirecting or absorbing every photon. The result, a patch of space where a brilliant disk should be but isn't. It's not just dim, it's dark in a way natural physics can't explain, like finding a city at night with no streetlights, just an unnatural void where the glow ought to be. Then there's the more exotic and terrifying idea, a photon cage. Imagine a structure built not to collect energy, but to imprison it, a lattice of mirrors or gravitational lenses trapping light in endless orbits around the black hole. No radiation escapes, no hints reach us, just a perfect engineered darkness. From Earth, such a cage would appear as a star that used to flicker until one day it didn't. No dimming, no fading, just silence. But why would anyone do this? One word: stealth. In a universe where advanced civilizations might view each other as threats, hiding your energy signature could be survival. Or perhaps it's about control, taming a black hole's fury so completely that you decide when and if light escapes. The implications shudder through astrophysics. We already search for black holes by their X-ray screams. What if the most advanced civilizations are the ones we can't see, their power sources deliberately muted? Of course, nature has its own light-blocking tricks. Some black holes go quiet when their accretion disks thin out. But a megastructure's signature would be different, unnaturally abrupt, lacking the telltale heat of lingering gas. That's why surveys like the Event Horizon Telescope don't just image black holes, they study their silences, because in the gaps between the cosmic noise, something might be listening back or deliberately hiding. The chilling thought, if a civilization can cage light itself, then the darkest patches of space might not be empty, they might be occupied. And the thing about perfect shadows is this: you never know what's inside them until it decides to step into the light. Now let's push the boundaries of megastructures even further, beyond single stars and into the realm of cosmic engineering so vast it defies imagination. Take the Alderson disk, a theoretical construct so enormous it makes Dyson spheres look like child's play. Picture a solid plate, not just orbiting a star, but cradling it at the center like a dinner plate holding a glowing marble. This disk would stretch from the orbit of Venus to beyond Mars, with a surface area millions of times greater than Earth's. The star's gravity would pull equally from all sides, keeping it suspended in the center, while the disk's outer edges could host civilizations in perpetual twilight. But here's the mind-bending part. From afar, such a structure wouldn't just dim the star, it would erase it. Light emitted perpendicular to the disk's plane would be blocked entirely, leaving only a thin ring of illumination around the edges. To distant observers, the star might appear as a dark hole in space, encircled by a halo of fire. Then there's the ring world, a concept popularized by sci-fi author Larry Niven but grounded in real physics. Imagine a ribbon of material 1,000,000 miles wide, forming a perfect loop around a star at Earth's orbital distance. The inner surface could be habitable, bathed in perpetual daylight, while the outer shell would absorb waste heat. But unlike a Dyson swarm which blocks starlight intermittently, a ring world would cast a permanent, razor-thin shadow across the cosmos. From certain angles, it might look like a star wrapped in a dark belt, its light peeking out above and below. The sheer scale of these constructs raises staggering questions. What materials could withstand such forces? How would a civilization stabilize them against gravitational wobbles? And most hauntingly, if one exists, how would we even recognize it? Consider the engineering implications. An Alderson disk would need materials stronger than anything known to physics, likely forged from exotic matter or stabilized by artificial gravity. A ring world would require constant thrusters to prevent its star's slight asymmetries from sending it crashing inward. These aren't just megastructures, they're metastructures redefining what's possible in celestial mechanics. Yet their very audacity makes them detectable. A functioning ring world would irradiate absorbed starlight as infrared from its outer shell, while an Alderson disk might emit heat from its dark side in unnatural geometric patterns. But the most tantalizing clue would be their shadows. Natural debris disks like those around young stars scatter light unevenly. An Alderson disk or ring world, though, would block starlight with surgical precision. Telescopes might spot stars that vanish too cleanly, their light curves dropping into near total darkness without the diffuse edges of dust or gas. Or they could detect starlight bending around unseen edges, as if space itself had been snipped with scissors. Perhaps the wildest idea isn't just finding these structures, it's realizing they might already be hiding in plain sight. Some anomalously dim stars in galaxy surveys could be partially occluded by megastructures in oblique orientations, their true nature masked by our limited vantage point. Others might appear as infrared heat sources with no visible counterpart, their starlight swallowed by colossal artificial horizons. The search for these titanic constructs isn't just about satisfying curiosity. It's a test of our assumptions about intelligence's limits. If civilizations can reshape not just planets, not just stars, but entire solar systems into habitable landscapes, then the universe might be far stranger and far more crowded than we ever dreamed. And the next time a star's light winks out in some unexplainable way, we'll have to ask, is it a cosmic coincidence or the silhouette of something built? The Kardashev scale gives us a cosmic ruler to measure civilization's ambition not by borders or armies, but by energy. At its core, it asks, how much of the universe's power can a species harness? Type 1 civilizations master their planet's energy, sunlight, wind, geothermal. Type 2 command their entire star, and Type 3, they reign over galaxies. It's a spectrum that starts with flickering campfires and ends with bending starlight like clay. But here's the twist, megastructures aren't just trophies for advanced civilizations. They're survival tools. Consider a Type 2 civilization perched on the threshold of stellar control. Their planet's resources are dwindling, their energy hunger insatiable. A Dyson swarm isn't luxury, it's necessity. Imagine the scale, millions of solar collectors, each the size of continents, orbiting in precise formation. The energy output would dwarf anything fossil fuels or nuclear fission could offer, but the challenge is brutal. Not just engineering, physics itself pushes back. A single solar flare could vaporize swaths of the swarm. Gravity tugs at imperfect orbits, risking catastrophic collisions. And then there's the material science nightmare. Earth's entire iron reserves couldn't build a fraction of a Dyson structure. A Type 2 civilization would need to mine asteroids, dismantle planets, or invent materials that defy our understanding of strength and heat resistance. Yet the Kardashev scale hints at something deeper. Maybe megastructures aren't built all at once but grown layer by layer like coral reefs in space. Early stages might look like our fledgling satellite networks, just a few energy harvesting platforms. Over millennia, they multiply, evolving into dense swarms. By the time a civilization reaches Type 3, their megastructures could be as natural as breathing stellar engines nudging stars into optimal clusters, black hole farms humming in the void. But there's a darker interpretation. The scale assumes civilizations ascend smoothly, but history suggests otherwise. Every leap from wood to coal, from oil to reactors, has come with existential risks. A species capable of stellar engineering could also be one misstep from self-destruction. The same technology that builds Dyson Spheres might unleash runaway AI or gravitational experiments that tear spacetime. This isn't just speculation, it's a lens to view our own future. Humanity's barely Type 0.7, yet we're already grappling with climate collapse and nuclear brinkmanship. The lesson: energy isn't just power, it's responsibility. The scale also forces us to rethink time. Our civilization measures progress in centuries. A Type 2 or 3 society might think in millennia or eons. A Dyson Sphere isn't a project with a deadline, it's a generational covenant. Imagine workers who'll never see completion, engineers designing for climates their great-great-grandchildren will inhabit. This shifts the very idea of ambition. Megastructures aren't just feats of engineering, they're testaments to patience, to civilizations that play the long game. So when we scan the cosmos for shadows of megastructures, we're not just hunting aliens. We're searching for proof that intelligence can outlast its own fragility, that somewhere a species has navigated the knife's edge between power and hubris. The silence of the universe might not mean we're alone. It might mean the hardest step isn't reaching for the stars but surviving the reach. Scientists don't just stumble upon alien megastructures, they hunt for them like cosmic detectives, piecing together clues hidden in starlight. One of the most powerful tools in their arsenal is the light curve, a graph that maps how a star's brightness changes over time. When a planet passes in front of its star, it creates a predictable dip, a symmetrical U-shape that repeats like clockwork. But a megastructure, that's where the graph goes wild. Imagine a light curve with jagged edges, sudden drops, or irregular plateaus, patterns that don't fit nature's usual rhythms. These anomalies are the breadcrumbs that lead researchers to ask, is this dust or design? But light curves alone aren't enough. To rule out cosmic false alarms, scientists cross-examine the star's entire electromagnetic fingerprint. Infrared telescopes like NASA Spitzer or the James Webb Space Telescope scan for heat signatures. A Dyson Swarm, for instance, might absorb visible light but irradiate the energy as waste heat, glowing faintly in infrared. It's like holding your hand near a light bulb after it's turned off. You can't see the light anymore, but you still feel the warmth. Natural objects like dust clouds also emit infrared, but their heat is messier, less uniform. An engineered structure, though, its thermal signature would be suspiciously precise, like the difference between the glow of a campfire and the steady hum of a radiator. Then there's the hunt for unnatural radio emissions. Advanced civilizations might leak artificial signals, not as deliberate messages, but as byproducts of megastructure operations. Picture the hum of a massive energy grid or the pulse transmissions of orbital traffic control. Projects like the Breakthrough Listen initiative scour the cosmos for these technosignatures, filtering out natural radio noise from pulsars and quasars to isolate anything that sounds intentional. It's the cosmic equivalent of eavesdropping on a distant city's power grid, but perhaps the most tantalizing method involves starlight itself, not just its brightness but its polarization. When light scatters off natural dust or gas, its waves vibrate in predictable directions. A solid megastructure, though, would polarize light differently, like sunlight glinting off a mirrored surface. Telescopes equipped with polarimeters can detect these subtle shifts, turning starlight into a forensic tool. A star occluded by a rotating Dyson ring, for example, might flicker with a polarization pattern as regular as a lighthouse beam, betraying the presence of something unnaturally smooth and geometric. The challenge is separating the cosmic needles from the haystack. The universe is full of weirdness: stars that dim from interstellar comets, pulsars that mimic beacon-like signals, dust clouds that glow eerily in infrared. That's why astronomers don't rely on a single clue. They triangulate. A candidate megastructure might tick multiple boxes: irregular light curves plus unexplained infrared heat plus odd polarization. It's the combination that raises eyebrows, and the tools keep evolving. Upcoming missions like the European Space Agency's Pluto or the Vera C. Rubin Observatory will monitor millions of stars simultaneously, spotting anomalies in real time. Machine learning algorithms sift through petabytes of data, flagging anything that defies classification. The hope isn't just to find megastructures, it's to recognize the patterns of intelligence, the cosmic equivalent of spotting city lights on a dark planet. This isn't just about astronomy, it's about learning to read the universe in a new way. Every flicker, every whisper of heat, every polarized photon could be a stroke in a grander message, one that says you're not alone. And as our tools grow sharper, we're not just searching for shadows, we're learning to see in the dark. In the vast emptiness between stars, most cosmic wanderers obey the silent pull of gravity until Oumuamua came along. This strange, cigar-shaped object barreled into our solar system in 2017, the first known visitor from interstellar space. At first glance, it seemed like just another asteroid, albeit one moving alarmingly fast. But then astronomers noticed something bizarre. Oumuamua wasn't just coasting, it was accelerating as if pushed by an unseen force. Theories exploded. Maybe it was a comet venting gas, except no tail or debris was visible. Perhaps solar radiation pressure was nudging it, but its flat, pancake-like shape defied expectations. Then came the most electrifying idea. What if Oumuamua wasn't a rock at all? Harvard astrophysicist Avi Loeb famously suggested it could be artificial, a light sail from another civilization using starlight as propulsion. The numbers almost fit. A thin, reflective sheet of material could explain both the acceleration and its unusual brightness variations, like sunlight glinting off a spinning piece of metal. The implications were staggering, a relic of alien engineering drifting through our cosmic backyard, but science demands rigor. Further analysis leaned toward natural explanations. Outgassing from hidden ice pockets might have given Oumuamua its kick without visible dust. Its tumbling motion and reddish hue matched known asteroids. Most tellingly, subsequent surveys found no radio signals or other technosignatures. The verdict: probably not a megastructure, but that doesn't make it ordinary. Oumuamua's real legacy lies in the questions it forced us to ask. Why shouldn't we consider artificial origins for cosmic oddities? The universe is under no obligation to conform to our assumptions. Every unexplained phenomenon is a chance to stretch our imaginations, to wonder if the line between natural and artificial might blur in ways we haven't yet dreamed. And the next Oumuamua, it could already be on its way. New telescopes like the Vera C. Rubin Observatory will scan the skies for interstellar interlopers, armed with hard-won lessons from this first enigmatic guest. Whether natural or not, Oumuamua taught us one thing: the cosmos is full of surprises, and sometimes the most ordinary-looking visitor might be the one that changes everything. The universe doesn't stand still, and neither would alien megastructures. Over millennia, these colossal constructs wouldn't just exist, they'd evolve, adapt, even multiply. Thanks to advanced simulations, we can peer into that future, watching how hypothetical Dyson Swarms, Matrioshka Brains, and stellar engines might transform, and how their shadows would shift across the cosmos. Picture a Dyson Swarm in its infancy, a few scattered solar collectors orbiting a star, causing barely perceptible dips in brightness. Fast forward 1,000 years. Now the swarm has grown denser, its components multiplying into billions, forming intricate lattices that fracture starlight into erratic patterns. Simulations show this phase would make the star flicker like a faulty neon sign, its light curves jagged with unpredictable dips. Some models even suggest advanced civilizations might optimize their swarms into fractal designs, geometric patterns repeating at smaller and smaller scales to maximize energy capture while minimizing collisions. The result, a star that doesn't just dim, it pulses, its light governed by an artificial rhythm. But evolution doesn't stop there. Take a Matrioshka brain, those nested computational shells around a star. Early iterations might leak heat unevenly, glowing in infrared like a misshapen ember. Over time, simulations predict the outer layers would grow more efficient, recycling waste heat with near-perfect precision. The star's visible light would vanish almost completely, replaced by a cold, uniform infrared halo. To telescopes, it'd look less like a star and more like a dark void with a faint thermal whisper. Some models even explore cascading Matrioshka brains, where multiple stars in a cluster are encased, their computational networks linked into a galaxy-spanning supermind. The combined infrared glow of such a system would stand out against the cosmic backdrop like a glowing fingerprint. Then there's the wild card, self-replicating megastructures. Imagine a civilization that builds not just for its own needs, but for exponential growth. Tiny robot probes programmed to harvest asteroids and assemble new solar collectors could spread like cosmic algae, doubling their numbers every few centuries. Simulations of this scenario are breathtaking and unsettling. Within tens of thousands of years, entire star systems could be dismantled, their materials repurposed into expanding megastructure swarms. The light-blocking effects would escalate from occasional dimming to total occlusion as stars vanish behind ever-thickening veils of machinery. Astronomers call this hypothetical endpoint the Fermi bubble, a region of space where starlight is systematically replaced by the waste heat of endless industry. Of course, nature has its own timelines. Stars age, galaxies collide, black holes merge. Simulations factor in these cosmic forces too. A stellar engine nudging a star across the Milky Way would leave a gravitational wake, subtly distorting the paths of nearby stars over eons. A Dyson swarm around a dying red giant might abruptly reconfigure as the star swells, its panels retreating like sailors fleeing a rising tide. Some models even explore legacy megastructures, abandoned constructs still blocking light long after their builders are gone, their shadows drifting like tombstones through the void. What makes these simulations so valuable isn't just their spectacle. They're training wheels for our telescopes. By predicting how megastructures might morph over centuries, we learn what signatures to prioritize, whether it's the infrared glow of a mature swarm or the gravitational ripples of a star under propulsion. The universe is a slow-moving canvas, and these models let us fast forward, spotting the brushstrokes of intelligence before they're complete, because out there in the dark someone or something might already be building. And when their shadows finally stretch far enough for us to see, we'll need to recognize them for what they are, not cosmic accidents, not natural wonders, but the deliberate, patient work of minds that think in millennia. Harnessing the power of an entire star sounds like science fiction until you realize humanity is already laying the groundwork. Imagine solar farms not just dotting deserts but encasing the sun itself, capturing every drop of its energy. The benefits are staggering: unlimited clean power, the ability to terraform planets at will, and a ticket to interstellar expansion. But here's the existential catch: building megastructures doesn't just change our future, It announces our presence to the cosmos in a way we can't take back. Consider the energy payoff first. A partial Dyson swarm could meet Earth's current energy demands 1 billion times over, ending resource wars and climate crises in one stroke. We're not just talking about powering cities. This is the kind of energy that could melt asteroids into habitable orbitals, fuel AI civilizations for millennia, or even propel generational ships to nearby stars. The technological spin-offs alone would redefine human potential. Advanced materials needed to withstand stellar radiation could revolutionize medicine. Space-based manufacturing could birth alloys and polymers beyond our imagination. Megastructures aren't just power plants, they're engines of societal evolution. Yet every beacon has its shadow. The same infrared signature that makes Dyson Swarms detectable across galaxies would function like a cosmic flare gun, broadcasting, "We are here." To anyone watching, and history isn't kind to civilizations that advertise their location to more advanced neighbors. The dark forest hypothesis, a chilling answer to the Fermi Paradox, suggests the universe might be full of predators where survival means staying silent. By lighting up our solar system with megastructures, we'd be breaking that silence in the loudest way possible. Even if hostile aliens aren't a concern, attracting attention from a Type 3 civilization could reduce humanity to a curiosity, or worse, a resource. There's a middle path, though: stealth megastructures. Instead of fully enveloping the sun, we could build sparse, irregular arrays that mimic natural dust clouds, or use metamaterials to scatter waste heat in untraceable patterns. The energy yield would be lower, but so would the risk. Alternatively, we might focus on black hole energy farms harnessing the gravitational fury of singularities, which leak far less detectable radiation than stars. These wouldn't be megastructures in the classic sense, but they'd offer power without the spotlight. The ethical choice hinges on two questions: is survival worth stagnation? And is caution just another word for fear? The universe rewards boldness but also punishes recklessness. Perhaps the answer isn't whether to build, but when and how visibly. A civilization that builds megastructures isn't just harvesting energy. It's making a statement about its place in the cosmos, and that statement could echo forever. What if the reason we haven't found alien megastructures isn't because they don't exist, but because they're hiding from us? This unsettling idea lies at the heart of the zoo hypothesis, a concept first proposed by radio astronomer John Ball in the 1970s. Imagine an advanced civilization observing Earth like visitors at a wildlife preserve, deliberately concealing their presence to avoid interfering with our development. Now scale that up to cosmic proportions, entire megastructures shrouded by technology so sophisticated they render entire star systems invisible. It's not just about staying quiet, it's about engineering shadows so perfect, even our best telescopes see only empty space where civilization should be. The mechanics of such camouflage boggle the mind. A Type 3 civilization could employ gravitational lensing to bend starlight around their megastructures, creating the illusion of nothingness. Or they might use metamaterials, exotic substances that refract light in unnatural ways to scatter their infrared waste heat into undetectable noise. Even more radical, they could manipulate space-time itself, creating optical cloaks that divert photons like water flowing around a rock. To outside observers, their Dyson Swarms or Matrioshka Brains wouldn't just be invisible, they'd be physically erased from the cosmic record, their stars appearing untouched despite humming with activity. But why go to such lengths? The motivations range from benevolent to chilling. Perhaps advanced species adhere to a universal prime directive, avoiding contact until lesser civilizations reach a technological threshold. Or maybe they're hiding from something worse, a predatory interstellar force that exterminates noisy upstarts. The darkest interpretation: we're not the zoo visitors. We're the exhibit, our planet preserved as a living museum while our keepers remain unseen behind one-way cosmic glass. The zoo hypothesis flips the megastructure search on its head. Instead of scanning for anomalies, we might need to question why certain regions of space seem suspiciously ordinary. Stars that statistically should have planets but don't. Galactic voids where infrared backgrounds mysteriously drop off. These could be the artifacts of perfect concealment, the equivalent of finding a hidden door because the wallpaper is too smooth. Astronomers have already noted odd, cold spots in cosmic microwave maps, areas curiously devoid of the expected thermal noise. Natural explanations exist, but the possibility remains. We might be surrounded by cloaked giants, their presence revealed only by the absence of what should be there. This isn't just paranoia, it's a survival strategy written into our own future. Humanity's first tentative steps toward stealth megastructures already exist in proposals like black bubble satellites designed to absorb all incident light. If we're considering self-concealment after mere centuries of technological growth, what might civilizations millennia older have built? The universe's silence might not mean emptiness. It could be a tapestry of civilizations holding their breath, each waiting for the other to blink first. And in that stillness, the hunt for megastructures becomes more than science. It's a game of cosmic hide and seek where the stakes are existence itself. The universe loves playing tricks on us, especially when it comes to missing starlight. While alien megastructures capture our imagination, the cosmos has plenty of natural phenomena up its sleeve that can mimic their eerie signatures. Take rogue planets, for instance. These lonely worlds, flung from their home systems by gravitational chaos, drift through interstellar space like cosmic ghosts. But when one passes in front of a distant star, the effect can be dramatic, especially if it's a gas giant with a thick ring system or a trailing swarm of moons. The result, a sudden, lopsided dimming that looks unsettlingly artificial. Unlike orderly planetary transits, these rogue interludes are unpredictable, irregular, and often one-time events, leaving astronomers scratching their heads long after the shadow has passed. Then there's the enigma of dark matter. We know it's out there, weaving invisible gravitational webs through the cosmos, but what if it occasionally clumps in ways we can't yet predict? Hypothetical dark matter structures like dense hair filaments or microscopic primordial black holes could bend starlight like a lens, creating brief, unexplained dimming effects. Unlike the clean shadows of megastructures, these distortions would warp the star's image, stretching it into odd shapes or creating duplicate mirages like looking at a street lamp through frosted glass. Even more perplexing are the quirks of stellar physics we've yet to unravel. Some stars, particularly young ones, are surrounded by colossal magnetic storms or hyperactive plasma loops that can erupt without warning. These eruptions don't just flicker starlight, they sometimes hurl opaque curtains of charged particles into space, casting shadows that linger for months. Other stars might be cloaked in vast, uneven debris disks, leftovers from ancient collisions, that orbit at bizarre angles, creating erratic dimming patterns. The star O Microscopii, for example, dims by up to 30% at random intervals, its light filtered through a chaotic whirlwind of planetary rubble. And let's not overlook the cosmic imposters lurking in our own backyard. Dense knots of interstellar dust drifting between us and distant stars can act like celestial frosted glass, subtly dimming and reddening starlight in ways that mimic partial Dyson swarms. These dust clouds aren't uniform, they're clumpy, with dense patches that block more light than others, creating irregular dips in brightness, the key giveaway. Dust scatters blue light more than red, so stars dimmed by natural debris look like they've been filtered through smoke. Megastructures, by contrast, would block all colors equally, leaving the star's hue unchanged even as it fades. The real challenge isn't just spotting anomalies, it's learning the universe's vast repertoire of illusions. Every time a star winks at us inexplicably, we're forced to ask, is this nature's sleight of hand or evidence of a hand we've never shaken? The answer might lie in patience. Over decades of observation, natural causes reveal their patterns, dust disperses, storms quiet, rogue planets move on. But a megastructure's shadow, that's a performance with no final curtain. It lingers, evolves, and perhaps, just perhaps, waits for us to understand the difference between a cosmic coincidence and a signal hidden in plain sight. The hunt for alien megastructures is about to leap into hyperdrive, thanks to a new generation of telescopes designed to see farther, sharper, and stranger than ever before. Take the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, set to begin scanning the skies in the next few years. With its 3,200 megapixel camera, the largest ever built, this beast of an observatory will photograph the entire visible southern sky every few nights, spotting changes so subtle they'd slip past other telescopes. Imagine having a time lapse of the cosmos where every flicker, every hiccup in starlight gets flagged for review. The LSST won't just spot Tabby's star-like anomalies, it could find hundreds of them, mapping their weirdness with unprecedented precision. Then there's the James Webb Space Telescope, already rewriting the rules of infrared astronomy. While Hubble showed us the universe in visible light, Webb peers into the heat signatures of the cosmos, the exact wavelengths where Dyson Spheres and Matrioshka Brains would leak waste energy. Its instruments are so sensitive they could detect the thermal glow of a megastructure around a star hundreds of light-years away, even if the structure itself blocks 99% of visible light. Picture this, a star that looks utterly ordinary in optical telescopes but blazes like a bonfire in Webb's infrared eyes. That mismatch, visible darkness paired with infrared brilliance, is the hallmark of engineered energy capture, and Webb is the first telescope capable of spotting it at scale. But the real game changer might be the European Space Agency's Pluto mission, launching in the late 2020s. Unlike most planet hunters that focus on single stars, Pluto will monitor millions simultaneously, hunting not just for planets but for the irregular, jagged dimming of megastructures in motion. Its cameras can detect brightness changes as tiny as 0.0001%, sensitive enough to spot a swarm of solar panels the size of Texas passing in front of a distant sun. And because Pluto will stare at the same stars for years, it could catch the slow, deliberate dimming of a Kardashev thruster nudging a star across millennia, or the incremental construction of a Dyson Swarm as new panels blot out starlight in fits and starts. On the horizon, even wilder tools await. The Breakthrough Starshot initiative envisions 1,000-mile wide arrays of ground-based lasers acting as interstellar radar, pinging nearby stars with pulses that could reflect off alien megastructures like echoes in a canyon. Meanwhile, projects like the Square Kilometre Array radio telescope will listen for the hum of megastructure activity, not deliberate messages, but the accidental buzz of colossal energy grids or orbital traffic control. The beauty of these next-gen tools isn't just their power, it's their synergy. LSST will flag the weird stars, Webb will dissect their heat signatures, Pluto will track their rhythms, and Starshot might one day ping them. Together, they form a net so fine that nothing, not a cloaked Dyson shell, not a drifting Matrioshka brain, not even a star being towed across the galaxy should slip through. And if, after all that, the cosmos still seems silent, that silence itself becomes data. Either we're alone or we're missing something fundamental about how intelligence manifests in the universe. But with these eyes on the sky, we're finally giving the cosmos a chance to answer. Long before astronomers began scanning the skies for anomalous starlight, science fiction was already dreaming up megastructures on scales that dwarfed planets. The concept of a Dyson sphere first leaped from scientific journals into pop culture in the 1960s, just years after Freeman Dyson's original paper, when author Olaf Stapledon's visionary novel, Star Maker, described entire civilizations encasing stars to harness their energy. This wasn't just world building, it was galaxy building, planting the seed for a trope that would reshape how we imagine advanced alien societies. Hollywood quickly seized the visual drama of these cosmic constructs. The iconic 1997 film Star Trek Generations featured a fractured Dyson sphere as a plot device, a broken shell surrounding a star, its sheer scale emphasizing the technological might of its vanished builders. Meanwhile, games like Halo and Destiny turned Dyson Swarms into playgrounds for interstellar warfare, where players battle amid orbiting solar collectors and habitation rings. These depictions do more than entertain. They embed the idea that a civilization's ambition can be measured by the shadows it casts across stars. But the most fascinating evolution lies in how sci-fi grapples with the humanity of megastructures. In Liu Cixin's The Three-Body Problem trilogy, an alien civilization constructs a Dyson swarm not out of triumph but desperation, their dying star forcing them into a nomadic existence, harvesting energy while fleeing cosmic cataclysms. Here, the megastructure isn't a trophy of superiority. It's a survival raft echoing our own anxieties about climate collapse and resource scarcity. Video games like Stellaris take this further, letting players become the architects of these colossal projects, facing dilemmas like ecological backlash or rebellions among populations living in the swarm's shadow. Even music and art have been captivated by the aesthetic of stellar engineering. Album covers from bands like Coheed and Cambria depict fragmented Dyson rings, while digital artists render Matrioshka Brains as glowing, fractal labyrinths, modern-day cathedrals to cosmic computation. These creations blur the line between science and myth, framing megastructures not just as engineering feats, but as cultural monuments. When artist John Hassel's Last Night the Moon Came Dropping Its Clothes in the Street sonically interprets a Dyson Spheres infrared hum, it turns astrophysics into poetry. This cultural feedback loop is where things get really meta. Sci-fi's portrayals influence real science, inspiring researchers to refine their search parameters. After Star Trek popularized the idea of Dyson spheres, astronomers began seriously modeling how such constructs might appear in telescope data. Games like Elite Dangerous, which simulate galaxy exploration with realistic physics, have even crowdsourced players to flag real-world star systems with anomalous dimming. The line between fiction and discovery has never been thinner because every time a writer dreams up a new megastructure, they're handing scientists a new hypothesis to test. Yet pop culture's greatest contribution might be its willingness to imagine failure. For every gleaming Dyson sphere in fiction, there's a derelict one, abandoned husks orbiting dead stars like the ruins of Babel in space. These cautionary tales remind us that megastructures aren't just about power, they're about vulnerability. A civilization that builds them is betting its survival on technologies that could outlast their creators, leaving behind cosmic gravestones visible across millennia. When we look up at strange dimming stars, we're not just hunting aliens. We're rehearsing our own future, one where the stories we tell today might become the artifacts someone else discovers tomorrow. The search for alien megastructures isn't just about solving cosmic mysteries, it's about rewriting what we thought was possible. Every unexplained dimming star, every anomalous infrared glow, is a crack in the door of our understanding, hinting at civilizations that might have transcended the limits of planet-bound life. Whether it's a Dyson swarm harvesting a star's energy, a Matrioshka brain turning sunlight into computation, or a Kardashev thruster pushing a sun across the galaxy, these constructs challenge us to rethink intelligence itself. They force us to ask, if a species can bend starlight to its will, what else might it be capable of? Yet for all the tantalizing clues, the universe keeps its secrets close. Tabby's star, rogue planets, dust clouds, each anomaly teaches us to be better cosmic detectives, to separate nature's quirks from the fingerprints of design. And as our telescopes grow sharper, so does the thrill of the hunt. Projects like the Vera Rubin Observatory and the James Webb Space Telescope aren't just tools, they're time machines, letting us scan the cosmos for echoes of engineering that might have begun before Earth even formed. But here's the most exhilarating part: this search belongs to everyone. You don't need a PhD to gaze up at the night sky and wonder. Every curious mind, whether you're a seasoned astronomer or someone who just loves a good sci-fi story, has a role in this grand puzzle. Maybe the next big breakthrough won't come from a lab, but from someone spotting a strange pattern in public telescope data, or asking a question no one else thought to ask. So keep looking up, stay skeptical, stay bold, and most of all, stay wildly curious. The universe is under no obligation to make sense to us yet, and who knows? The next time a star flickers inexplicably, it might not just be a cosmic coincidence. It could be a signal, a signpost, a message from across the light years saying, "You're not alone." Now it's your turn. What's your wildest theory about these cosmic megastructures? Drop your thoughts in the comments, because the next great idea might just come from you. And remember, the stars aren't just points of light, they're questions waiting to be answered. Let's find them together.